Okay, so thanks for the introduction. I am Matt Amy, and I'm going to talk about the experience of me and my co-authors on writing a verified reversible circuit compiler. And it's actually very similar to the Everest project that we heard about this morning, but on a much smaller scale, because there's only 3 of us. So even though I'm going to be talking about reversible circuits, I'm going to start off talking about quantum computing, which really informs this whole project. So we've all heard the doom and gloom stories about quantum computing, or at least I have because I'm in quantum computing. And basically, it's going to destroy all encryption. We're never going to be secure and stuff like that. But the reality is that isn't necessarily the case because there's a huge amount of overhead that goes into actually implementing quantum algorithms. So you get a lot of overhead from 2 areas, one of which is implementing classical functions in a reversible way so that you can do them in superposition, and the other is error correction. I'm not going to talk about the error correction, just the first part. So, what is reversible computing? The basic idea is that obviously, as the name says, all your computations need to be reversible. They need to be invertible. And it's not just a global condition, it's also a local condition. So every operation you do in the computation needs to be reversible. So the classic example is the AND function. If you have x and y is equal to 0, you don't know anything about x and y. So if you just have the output of that function, you can't get your inputs back. It's irreversible. And the other problem is you can't reuse memory. So that ends up being a big problem when you're compiling these circuits. Because once you've used a bit, once you've computed something into a bit, you have to explicitly uncompute it. Otherwise, it's not locally reversible. So what you actually have to do to make functions reversible for the most part is to embed them in a larger state space. So the Toffoli gate is the reversible analog of the AND gate. And what it does, you add an extra bit, and then it XORs the AND of the first 2 bits into the 3rd bit. So if the 3rd bit is 0, then it's actually just the AND function. So naively, if you have a classical circuit, you could make it reversible just by replacing all the AND gates with these Toffoli gates, using a new bit every time, and that's called using an ancilla in quantum computing. But the problem with this strategy is you use an amount of space that's linear in the number of AND gates. So time and space complexity collapse together, right? Which is not good. So Charlie Bennett came up with this trick, they call it, where what you'll do is you'll copy the output of a function onto a new bit, and then you'll uncompute everything, return the entire state back to its initial state. So this is an example of a reversible circuit. Bits are on the horizontal lines and time flows left to right. So this computes Bennett's trick for some function f. Basically, you have your forward circuit, the u of f, that computes f into the first ancilla. Then you copy into the second ancilla and just run that initial circuit backwards to get back to your initial state. So if you've heard about quantum compilers and quantum programming languages, and you've wondered why they do that because we don't actually have quantum computers, it's really for this problem of resource estimation. So we want to figure out how much overhead there actually is in a quantum algorithm, right? And that's really all quantum compilers do at the moment. So a typical design flow for figuring out the resources required for a quantum algorithm is you would write out high-level code, using irreversible operations, for example. Then your compiler would turn these irreversible functions into reversible circuits, combine everything together, and then spit you out a circuit, which you can then use to estimate the amount of error correction you need, which will be more overhead. And just to give you an idea of how much overhead you actually get from this red segment here, expanding classical functions into reversible, the quantum linear systems algorithm expands every 1 bit into 1,000,000 bits in one estimate, which is huge. It's terrible. So we really want to get the space use down for these reversible algorithms. Okay, but I'm talking about verifying a compiler, so why would we want to do that? The main reason is that these resource estimates vary wildly, like really wildly, to the point where no one in the field has any confidence that the different resource estimates are actually correct. Well, if you wrote the compiler, you have confidence, but other people don't. So, and the other problem is you can't use classical hardware verification techniques. We tried this and it doesn't scale because reversible circuits, they aren't like classical circuits. They're more like assembly language. You compile a special purpose thing, a huge circuit, you know, for every function, and you don't tend to reuse these circuits. So this is just an example of one round of SHA-256 as a reversible circuit. It's this huge, ugly thing that doesn't really have different components. You can verify separately. Okay, so what we did is we developed this formally verified reversible circuit compiler using F*, like Everest, and we do actually have a mechanism for program verification as well as the compiler verification, where we can check assertions using just standard BDD-based techniques. Nothing too interesting there, so I'm only going to talk about the verification of the compiler. So this is an overview of the architecture of our compiler. Everything inside the dotted box here is the F* code that forms the core of our compiler. It compiles down to F# code that hooks into an older compiler that was made for reversible circuits, so that's why it's not the whole compiler itself, but yeah. So let's talk about the source language first. This is an example of Rev's program, which is our source language. It's basically an F# metaprogram that returns a quotation, and we use this so that we can generate different size circuits effectively. And it has, you know, standard things like functions, Boolean expressions, assignments, that kind of stuff. But the one thing to note is that all control is completely static. And we didn't do that just because we're lazy. We did that because it's a restriction of our target architecture quantum circuits. Effectively, if you allow control to be based on the value of bits, you have to measure them, and then everything decoheres. So it compiles to effectively straight line programs. So this is what the 4-bit adder compiles to with reverse. Yeah, don't worry about the particular gates there. It's just the idea of the straight line program. No, you know, moving around and stuff like that. So what we do is first we take the Revs program and we do this thing we call parameter inference, which just figures out the size of different registers based on their use to get an annotated version of Revs. And then after that, we compile it down to this thing we call the Boolean abstract machine. And we do that through partial evaluation. So what this Boolean abstract machine is, it's you have exactly one operation, which is assignment. And the L value needs to be a new location, or at least a zero-valued location, in order for it to be reversible. And the right-hand side can just be any Boolean expression. And so what you end up with is something that looks a lot like single static assignment form. But the reason we did it as partial evaluation and not just SSA transformation is it unified the semantics with the transformation. So that reduced basically one of the things that we'd have to verify. We do the transformation just as we do the interpretation of the language. So, okay. So then the Boolean abstract machine gets compiled down to reversible circuits. And it does this a couple different ways. And the reason we did that was there are different benefits to each of the methods of compilation. But I'm only really going to talk about one in the interest of time. That's the eager cleanup version. The rest is all just kind of standard techniques, but this is something new that we added to this compiler. So when you look at the straight line program here, after we've done the partial evaluation, we see that we never actually use carry 1 again, obviously, after it's used to compute carry 2. So we could garbage collect that, right, and reuse it for carry 3. The problem is, since this is reversible computing, we can't just 0 carry 1. So we have to actually uncompute that. And we solved this problem by associating with each location a cleanup expression, which is basically just an expression that we can XOR into that location to get back the 0 value. So just as an example, I got rid of the other assignments and added some clean expressions here. So before the first statement, the cleanup expressions for each of the bits, on the right it should be C3, not C1, is 0. After we assign C1, cleanup expression is now A0 and B0. Then we assigned C2, and again we changed the cleanup expression. Now when we clean C1, we've actually changed the value of C1, so those references to C1 in line 3 are no longer valid. We need to find a new cleanup expression. We basically just substitute the old cleanup value for C1 into the cleanup value for C2. Right. And then we continue on. And the problem with this is, obviously, these cleanup expressions keep growing as your program goes along, right? So what we did is we truncate it after a certain point and just say, we can't clean this anymore. It's, that bit's gone. We can't use it again. And I haven't talked about verification really at all yet, so let's talk a bit about that. We verified reverse in F star, and reverse is about 2,000 lines of code. It's very small, but we achieved about like a 1-to-1 ratio of proof code to just program code. And we did that in about 1 person month, which is pretty good considering we don't really have experience in verification, really. I've played around with Coq a bit and Agda, but never anything serious. So yeah, it was very easy to pick up F star, which I liked. So the main theorems that we proved that circuit synthesis obviously produces the correct output, that we clean all intermediate ancillas. There's nothing laying around in the program that we haven't cleaned. We do this by doing a final level of Bennett's trick, basically, after the whole thing. And each abstract machine compiler preserves the semantics, of course. All optimizations are correct, blah, 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 that kind of stuff. And rather than go through the proofs for all of those things, because they're pretty standard, I believe, I'm going to talk about one thing that was kind of cool. When we were verifying the Bennett trick, we actually, being forced to prove it formally to the F star compiler, gave us an idea for a generalized version of Bennett's trick. Because we had never really thought about what the conditions, that everyone just knows Bennett's trick is correct. So when we were proving this, we had to show that it works because the middle gate doesn't affect the bits that are being cleaned. So then we found the same proof basically works for this other more general method where we don't have this strict separation between compute, copy, uncompute. So we can do this kind of thing, where as long as the bits that are being cleaned, I think, or as long as the bits that aren't being cleaned aren't controls, basically the black dots in the computing circuit, we can uncompute everything except for A, obviously. So just to give you an idea, this is what the proof code looks like for those two theorems. It's pretty simple, just 4 lemmas. I mean, those lemmas themselves are not simple, but it's nice in F star for someone who's not a verification expert that you can just throw a whole bunch of lemmas in and hope the SMT solver comes up with something. So I thought that was interesting. So we did some experiments just to see how it compared to kind of the previous state-of-the-art eagerly cleaning reversible circuit compiler, which was, what this project was based on in the end. And for the most part, we got very similar results. In some cases, we actually did better. So, yeah. And in conclusion, I didn't talk about this in the talk, but we formalized revs. It was not a formal language before, but obviously we had to give it semantics to prove things about it. We designed a new method of eagerly cleaning for reversible circuits, and we implemented and verified this in F star. And the takeaways, I guess, being part of the verification community, you probably all already believe this, but what I thought was interesting was it seems like proving theorems about real code now is not unreasonably difficult, like everyone else says it is. We did this quite fast, I believe, in about a month. And part of that was because we designed the code in such a way so that the actual difficult parts didn't branch out into other areas of our code. It was very self-contained for the difficult parts of the proof. So, thanks. Any questions?
Questions? So it looks like you use the verifier as a black box, the SMT solver, right?
Yeah.
And so did you get any time in the situation when it would just run forever, and what did you do about it? Or did actually everything go smoothly? And
No, so F star has a timeout for the calls to Z3. And yeah, we ran into a lot of cases when it would just time out, and you would either have to increase the time or go back and change our proofs and stuff. One of the proofs takes a very long time to verify, like an hour type thing. So that's not great, but maybe we can use some of the techniques from the Everest talk this morning to speed it up.
So, but you never got feedback why, or what should you change?
Yeah, so I mean, that is definitely one thing. It's very hard to tell why a proof fails. So you kind of develop a style where you try to prove assertions, or at least that's what we did. You just try to prove individual assertions that will lead to the end of your proof, and you just do that kind of step by step. Otherwise, you have no idea. It just fails.
Thank you, and if there are no more questions, then we can come to the last talk.